So let's take a look at a sample problem from Module 6.1. So in this example problem here, in our problem statement, we can see that we have a water tank that is subjected to a force, PT, from a blast. The stiffness is given to us as 8.2 kips per inch. The natural period is given to us as 1.12 seconds, and the pulse duration is given to us as 0.08. They ask us to determine the shear force and bending moment at the base of the tower with no damping. So we have this diagram over here. Here's our water tank. You can see this height up here, 80 feet from the ground. And we have our load P of T right there. That's the force from the blast. And we have our diagram given to us over here. We have our P in kips. And over here we have our time in seconds. So now that we have the opportunity to read through the problem statement, look at the given diagram, understand what they've given us in the problem and what they're asking us to find, we can now create our setup page. So here we have our example. We have a water tank subjected to a force PT from a blast. They want to determine the shear force, bending moment at the base of the tower with no damping. So we write down our givens here. Well, they give us our stiffness K is 8.2 kips per inch. They give us our natural period T sub n is equal to 1.12 seconds. And they give us our pulse duration T sub d is equal to 0.08. Redraw simplified version of my diagram over here. I have my P of T, I have my height here, and there's my water tower. I have my graph I redraw over here. Now the key equation I want to take a look at is the ratio here. And the reason I want to take a look at this ratio of TD to TN, or our pulse duration to our natural period, is to determine if we can assume an impulse. And we look at this here, we say take 0.08 divided by 1.2, and this is 0.071, which is less than our 0.25, so therefore we can assume an impulse. So from here we can begin our solution. So page 1 of our solution here, we have d sub I is equal to p times tau dt. So from this here, we can take the integral of both sides. The integral of di becomes I. And we have the integral from 0 to 0.8 for our limits of integration of p of t dt over here. And this comes from our textbook, equation 5.21 on page 123. We can reference back to that. Now from our graph, we have here is integrals under a curve. So we can create a t-chart from the information on the graph here. We can say, okay, when t is equal to 0, our p of t is 0. When t is equal to 0.02, our p of t is 40. When t is equal to 0.04, our p of t is 16. And when t is equal to 0.06, our p of t is 4. And finally, when t is equal to 0.08, our p of t is back to 0 again. Now what we realize is from our graph here, we have the fact that an integral is simply the area under a curve. We can recall this back from pre-calculus there. So the area under a curve we have here, so general form from the integral of a to b of f dt is approximately equal to b minus a, for our limits of integration right there, times f of a minus f of b over 2. So we can apply this approximation here to get the area under the curve from the information given to us in our chart and now our t-table over here. So that's exactly what we do is we can go back up this equation here from 5.21 on page 123 and we can use this approximation for the area under a curve here based on the information they gave us within that diagram and in our given table here that we've created from the diagram there. So what we have here is I is equal to 0 times 0 plus I have now 0.02 times 40 plus 0.02 times 16 plus 0.02 times 4 plus 0 times 0. So we do out the math here. We have 0 plus 0.02 times 40 is 0.8. 0.02 times 16 is 0.32. And 0.02 times 4 is 0.08. So that's the difference between the 0.02, where this is coming from, is the difference between each one of those. To go from 0.02 to 0.04, that's a 0.02. To go from 0.04 to 0.06, that's 0.02. To go from 0.06 to 0.08, that's 0.02. So that's where those 0.02s in this equation here come from. We do that, we can simplify this down a little bit now, and we find that I is equal to 1.2 kips times second. So with that information there, we can now move on to calculate our max displacement. So we have our general equation here for max displacement. Our u naught is equal to I over k times 2 pi over t sub n. So we have most of this information already given to us. We've just solved for our I term on the previous page. We have our T sub n here from the problem statement, and we have our K value from the problem statement there. So we can plug these guys into this above equation for our max displacement. When we do that, we get our U naught is equal to our 1.2 for our I over 8.2 from our K times 2 pi over 1.2 from our T sub n right there. We plug that in right there. We do out our unit analysis and double check to make sure, do that, everything cancels out, inches equals inch. That's a good double check for us to make sure everything was in the right units, we're using the right formulas. What we end up with at the end is U naught is equal to 0.821 in units of inches, which is what we found from our unit analysis. From there, we next want to calculate our equivalent force. So we have our general equation here, F naught is equal to K times our U naught, where again, we know our K value given the problem statement is 8.2 kips per inch. Where now we have our U naught from the previous slide for our solution there is 0.821 inches. So it's a straightforward and plug and chug to get our F naught here. F naught is equal to our 0.82 for our K, sorry, 8.2 kips per inch for our K value there, and our U value here of 0.821 inches. Plug that in, and we end up with our F naught is now equal to 6.73 kips. So from there, now that we have our F naught, we can do our shear and our moment calculations. So our F naught is equal to our V max here. So our F naught is equal to V max, so therefore our V max is equal to our max shear, which is 6.73 kips. So that's straightforward. And from there, our moment, our max moment here is equal to F naught times that distance right there, force times the distance of 80 feet here. So we have our F naught in kips. We have our distance in feet here, 6.73 kips times 80 feet. Our max moment is then calculated to be 538 kips times feet.